but it's just kind of, it's really more of an overview than it is, oh, that went, I thought it was gonna like ask me like, do you want to start recording? But no, it just kind of went for it. Yeah, so this is just gonna be a quick little review. If you have questions, just feel free to jump in. Again, it's just gonna be more of an overview about what we did and kind of a reminder with that. You have these slides as part of the course material, I believe, right? So if you look at course material on Google Classroom, Unit 1 fluid slides, these are the slides we've been using. You got all like 400 of them in there. It's a lot. Yeah, it's actually like 300, but still. So if you want to go more in depth, you have these, but here's just kind of an overview of everything that we did. So way back all the way in August, I think it was August, right? Yeah, we started August. Way back all the way in August, we started off the unit by kind of building up this model of fluids. And the way that we did this was I said, hey, take this balloon, get it inside of this bottle. In doing so and working through this, you guys kind of worked on different simulations, or not simulations, little demos with your material, and you kind of developed this model for fluids, this idea of how liquids and gases, how these work, how they function in order to do the things that we see. So you kind of explained what we saw in terms of these models. So we developed this model for fluids. Liquids and gases are fluids, things that flow. They have slightly different properties, but we said, hey, we can think of these objects as little tiny balls, little tiny particles that kind of bounce around. In a gas, they bounce all over the place. In a liquid, they're just kind of more closely put together and kind of closer together. And really the main ideas that we saw from this, the main things that we saw was, okay, when we have gases can be compressed. We did this little demo. I told you to do this demo. I don't know if you did it or not. But you had this syringe, you put the cap on it. One of them you put water in it. One of them you just had air in it. And you squished them. The air one you could compress. The liquid one, the one with water in it, you couldn't really compress it at all. So we're saying like, hey, air is compressible. Sorry, not just air. All gases are compressible. Whereas water or liquids cannot be compressed. They're going to be incompressible. So if you push them, they kind of have to go somewhere. They can't be kind of squeezed. We can't really change their volume by squeezing them. We said that gases and all liquids, they can flow. They have this ability to go from one thing to the other. They have this ability to flow. We said that they can fit and fill their container. Then kind of a difference we said is that gases are going to be less tightly packed. And this should be for gases and liquids. But we know that both of them have this ability to push on things and supply this pressure. So we saw that was kind of the reason how we were able to get this balloon filled up, is we had more pressure on the outside than we did on the inside of that bottle. The air on the outside was able to push on the balloon and inflate it. So we have this idea that gases can supply this pressure, they can push on objects. And yeah, when we look about liquids, we said liquids are incompressible. Same thing with that syringe. We filled up with water. We saw that we cannot compress it. So if we kind of push on one part of our liquid, the rest of the liquid has to go somewhere. We said liquids can also flow. They also fit their container. They are more tightly packed, which is kind of our rationale for why they're incompressible. There's not as much space between the particles. And again, they can supply a pressure on objects. Then what we did was we said, okay, well, we have this model for fluids. We have these particles that are kind of, doing their thing. Sometimes they're moving around. Sometimes, well, they are moving around. Sometimes they're close together. Sometimes there's not. If we change up the properties of how these particles are arranged, how many we have in a space, how much mass these particles have, then we said, hey, we are pretty much affecting the density of this object. So we had that idea, and then we defined this term of density. We said the density symbolized by that, some of us are calling it a P. It's a Greek letter rho, but it doesn't really matter. But we have this rho is equal to our mass divided by our volume. Density is equal to mass divided by the volume. And we said that we're going to have units of density of kilograms per meters cubed. Then what we did was we worked on this lab in Pivot. We had two labs. One of them, we were finding the density of a liquid. One of them, we were finding the density of the gas. And we were saying, okay, if it's more dense than its surroundings, it's going to sink. If it's less dense than its surroundings, it's going to float. That's what we did with the gas lab. And then with the liquid one, we kind of had this idea that was kind of cool. A lot of us used it, and a lot of us were able to say it well in the explanation of that lab. We said, hey, if you're going to graph mass per volume, the slope is going to be the density of that object. So we'd see like, hey, like your change in mass, your rise over your run, your change in volume is going to give us our density. That's going to be a constant number. And we said in that lab, that little Pivot lab, that if we are going to want to increase the accuracy of our density measurement, we can create this graph and find the slope. It'll let us, oh my gosh, what word am I looking for? it'll let us consider more points than just one mass measurement and one volume measurement, which will increase the accuracy of our data. So that's what we did then. Then what we said was, okay, well, if we look at this, if we use this density equation for something in real life, like calculating the density of air in our room, we can figure out like, hey, there's actually like a significant amount of mass from the air in this room. Like, so I did the dimensions in my room, and it was a Google form, and I was like, hey, figure out how much mass there is. I think it was like 18 kilograms or something of air, maybe something like that, around there, I don't know. But that's a significant amount of mass, and I was like, okay, why don't I feel this? Why don't we feel this mass of air that's around us? I had that video of me in the vacuum, or sorry, I wasn't in the vacuum, in the garbage bag. I went inside of a vacuum cleaner. I got myself sucked up. It was a terrible situation. I got stuck in the bag for 3 days. No, that wasn't that funny. So I was in the garbage bag, and then the vacuum was in there, sucked out the air that's in my immediate surroundings, and that's where I felt this push from my surroundings. I kind of felt the mass of this air, and we wanted to figure out why that was happening and how this would be different if we did it on the bottom of a valley versus the top of a mountain. So we kind of set up this experiment to see how does pressure change with the depth of the surroundings. So how does pressure in a fluid change with depth? So we did that lab, and we found that we have this linear relationship between pressure and depth. I have the equation on the next slide. And then what we argued also is that pressure is related to the density of the fluid, G, that gravitational constant, and the depth. So we said, like, we can kind of imagine the air, right? We say like, hey, this air is a fluid. It has a density. It has a volume. It has mass to it. If we're thinking about being on top of a mountain, there's significantly less air above us that is pushing down on us, causing this pressure. If we're on the bottom of a valley, we can say, hey, there's significantly more air above us. There's significantly more mass above us. So we have more of this pressure because there's this greater force pushing it down on us. We were also, it was kind of weird, but we said like, hey, yeah, this pressure, it seems like it's only going to push down. But if we think about how this fluid, specifically like liquid, we see it a little bit with gases where they'll push on each other, but specifically with fluids, we said, hey, this is incompressible. If we push down on the top, the fluids inside this kind of imaginary, this space that we're looking at has to go somewhere. So they're all going to kind of like push against each other, and they're really just going to push out in any direction that they can, which is why we're saying, hey, pressure doesn't just push downwards. We also have pressure that acts on the sides of our containers, on the sides of our wall, really any surface that we have, because of this incompressibility, because they're like kind of pushing into each other. This is going to push on all sides of our container and not just down, even though a lot of our argument is kind of us saying why it's pushing down. But we can extend that and say, if we think about those little particles, they're spreading out, they're pushing against all sides of our container. So pressure is really pushing on all sides, all walls of our surfaces. And then from that lab, from this relationship, we ended up with this equation that tells us the pressure is equal to some sort of initial, some sort of starting pressure, plus our rho GH, the pressure that's caused by that fluid, by the weight of the column of that fluid. Let's see, so I have a chat. Is it why we don't feel it? Because it's on all sides. Yeah, so we don't feel it because we have air in us. Yeah, that's a good question. So if we think about like why we don't feel the pressure from the atmosphere traditionally, is because, yeah, there's air pushing on all of us, right? Kind of in like all directions. So we have air that's kind of pushing out in all directions. So we kind of have like air pushing against air. When we take away kind of the air by us, also there's air inside of us that's causing this pressure. But yeah, when we take away kind of the air in our immediate surroundings, we have this ability to, right, there's nothing really pushing out as much as there is pushing in. So yeah, we can say like, hey, there's air in us that's kind of making it so we don't feel this pressure. There's air like right next to us that's pushing on all sides. Yeah, so we kind of have pushes from everywhere. When we take away the ability for some of these overall pushes, then we kind of increase our ability to push from the outside in. Yeah, so we have this pressure versus depth, where we said, okay, we have this relationship. P naught is kind of our starting pressure. Rho GH is the pressure from the depth of our fluid. We say from this equation, we have this kind of big idea that the same fluid at the same depth has the same pressure. And then we also define this. I think this is probably the one thing from the unit that is still like super confusing, and I feel bad about it. But we have this idea, this difference between gauge pressure and absolute pressure. So when we're looking at absolute pressure, here's kind of this image that helps a little bit with it. Absolute pressure is going to be a measurement from 0 pascals, this absolute vacuum where we have absolutely no particles and no pressure whatsoever at all. Absolute pressure is going to tell us, hey, on a scale where 0 is equal to 0, what is our pressure? Gauge pressure is going to be like, okay, let's pick some other location. Let's just call this 0 and see how our pressure compares above or below that local 0. A lot of the time, for the most part, that local 0 that we're going to have interest in is going to be the atmospheric pressure, so like the pressure around us. So we want to know, like, hey, what's our pressure based on atmospheric pressure? The reason why we'd want to know that is because, like, in everyday life, we know that atmospheric pressure, it just is acting on everything around us. If I was going to like blow up a balloon and I wanted to know, like, hey, how much pressure is in this balloon? If I included the pressure due to the atmosphere, I guess I could have blown up a balloon. Do I have balloons anymore? That doesn't really matter. That wouldn't have been a helpful visual. Y'all know what a balloon looks like. If I blew up that balloon, we'd probably just want to know, like, hey, how much pressure is this greater than atmospheric pressure? If I want to know how much pressure is in the balloon, it would be a little bit more interesting to know, how does my pressure compare to atmospheric pressure, as opposed to, yes, we have 1.0 times 10 to the 5th pascals from the atmosphere plus the pressure inside the balloon. It's a little bit more interesting for us to be like, hey, like, there is just this is a little bit, this is this much greater than atmospheric pressure. I was talking to somebody in AM support today, and I kind of made this analogy. I don't know if this is helpful or not. Use it if you want to, use it if you don't, or don't use it if you, use it regardless. No, use it if you want to, use it if you don't want to. But let's say, like, kind of if we're looking at this absolute versus gauge, this isn't a pressure example, but it's kind of an example of why we may want to do this, and kind of a little visual that's helpful based on other physics things we've done before. Let's say you're on top of, like, or you're on the 3rd floor of a building. This is going to be inside the building. I would pull up like the whiteboard so you could see that, but I don't know if that would show up in the recording. But let's say you're in this building and you pick up this ball and you're on the 3rd floor. You're happy, you're smiling. So you pick up this ball, and let's say that this ball is 1 meter above the floor. So if I was like, hey, what's the, and like, let's call this outside, let's call this like absolutely 0 meters. If I was like, hey, what's the pressure, or not the pressure, sorry. If I was like, hey, what's the height of this ball? You'd probably tell me, like, hey, compared to my local surroundings, compared to this local height that I have, where the bottom of this 3rd floor, you'd probably call that 0 meters, right, in your reference frame. You'd probably say, oh, well, the height of this ball is 1 meter. If we're going to use kind of terms that don't make any sense, that I'm making up on the spot, that'd be kind of like your gauge height. You're comparing it to something that's local, that's something around you. You don't really want to consider everything else, because that would just be annoying and it's not really a helpful measurement. Technically, if we look at this absolute height, again, a thing that I'm making up that doesn't really mean anything, but it kind of helps for this situation. If you look at like your absolute height, technically this ball is at 1 meter plus, I don't know, let's just say that a story is 3 meters plus 3 meters plus another 3 meters. Technically above this like absolute 0, not really the right use of absolute 0, but you know what I'm saying? Absolute 0 is a temperature measurement. But if we're looking at this absolute height, this 0 that is R0, like the most 0 we can go, technically you're at 10 meters. The ball is 10 meters in the air, but that measurement is immediately less helpful to you. Yeah, the higher it is, if you go higher, that's a negative depth, yeah. But yeah, so if we're looking at this, like, hey, this measurement right here of 1 meter, kind of your gauge height, is more helpful. Immediately you're saying, yes, I know that I'm at some height around me. I know that I have this height or this pressure surrounding me, but I want to know how it compares to what's going on locally, which is why we'd want to use this gauge pressure as opposed, yeah, I know how to add my bad stuff. Thanks, yeah. But yeah, so we'd say like, hey, sorry, I thought I had another floor, that's my bad. When I did it earlier, I was on the 4th floor, so I did 3, 3, 3, 1. I feel like I need to justify not knowing basic math, my bad. But yeah, so yeah, so we can say like, hey, locally, this is how much we are above this local 0, as opposed to based on this absolute scale. So same thing with pressure. We'd want to say like, hey, what's our pressure compared to everything around us, as opposed to like, what's this pressure compared to this scale where 0 is equal to 0. So I don't know if that was helpful or not. Maybe it was a helpful analogy. If it wasn't helpful and you felt good about it, well, that's okay. Don't worry about it. But yeah. All right, so moving on to the next part. Then we said, okay, we have these pressure differences with depth. So as the depth changes, we said that we have this difference in pressure. So as we go deeper, we are going to have a greater pressure. And we're thinking like, hey, why does this matter? What's really important about that? What's really going to happen with this phenomenon of pressure versus depth is going to be what causes a force in physics. It's going to be what causes our buoyant force. If we kind of look at this object, we know that all objects are going to have some sort of depth dimension. We don't have two-dimensional objects. When we put objects in a fluid, more specifically, we're going to look at like liquids, but I mean, you do have the buoyant force in gases. Like we have a buoyant force acting on us right now, but it's very small because the density of air is very small. But we are going to say like, hey, if we put something in a liquid, because it's going to be a little bit more visual, but any fluid, if we look at what's going on here, we say as the depth increases, the pressure is going to increase. So if we look at the top surface of our object, it is at a lower pressure than the bottom surface of our object. We said that pressure is going to be force divided by area. So if we look at what's going on here, over this bottom area, we have a greater force than we do on the top area. So if we look at like the net force acting on this, we have an overall, caused by the water, a greater upwards force acting on our object by the water. On the sides, we don't really see any side-to-side movement because we're saying, hey, the force over here is at the same depth as the force over there. So we're going to have the same pressure. It's just going to cancel each other out going up the object. Even if our object's not like symmetrical, right? We're looking at cubes. We're still going to see like overall, we're going to have like this net. If we sum up the sides and you do like a weird like summation, I believe that it'll cancel out and we won't really have a buoyant force going left to right. But for our purposes, we're just going to look at vertical upwards buoyant forces, which I'm pretty sure still is the only type of buoyant force. I don't know, actually. Oh no, and this is recorded. You have me on record saying I don't know. I don't think there's, right? Even if the objects are weirdly shaped, I'm pretty sure you have like some vectors that are canceling each other out. I don't actually. I should look into that. But yeah, so we have this buoyant force that is an upward force, an interaction between a fluid and our object. And what we're going to say is that it's always going to point upwards because of this pressure difference of our object. So then we can say, okay, this is our equation for the buoyant force, this rho, this density times the volume times g. The buoyant force is probably one of the most confusing equations because of just what's given to us in terms of the variables. It could mean a lot of different things, so we have to be very specific and very intentional when we're using our buoyant force equation. The density that is referenced in this equation is going to be the density of our surrounding fluid. So the density that our object is submerged in or is in, the density of the fluid that our object is in. The V in this equation is not going to be the full volume of our object. It's going to be the volume of our object that is submerged in the fluid. Or we kind of talked about last class, we could also call this the volume that our object is displacing of our fluid. So we have to think about how much of our object is actually inside of our fluid that we're looking at. If we're, or I'm not going to, nah, it's not that confusing, I don't know. But if we're looking like, hey, like this object, this pencil right here is in this sea of air right now, it's submerged in the air, then we'd say, okay, it's the full volume. That wasn't really that helpful. But if I had like a cup of water and I stuck my finger in the water, we'd only look at the volume of my finger that's in the water. We wouldn't look at my full volume because we just care about how much volume is submerged or how much volume is displaced. And then G is 9.8 meters per second squared. Same as per usual. And then to kind of use this buoyancy force, it's just a force just like every other force that we've dealt with. Really all that this boils down to is using Newton's second law. It just feels a little bit different because we don't usually see objects just kind of start floating upwards, right? So that's really the only difference, is that it looks a little bit weird because it's harder to see the interaction between our object and the fluid, but it's just like any other force. So what we have to do, this is kind of our, again, we've dealt with other examples with like tension forces, tension forces and normal forces, but this is kind of our simplest case if we're just thinking about putting an object in a fluid. Again, you can have other forces acting on it, but again, if we're just looking at the simplest case, if something's sinking, we'll say, hey, there's this net downwards force. That would mean that if we're putting it in a fluid, the only forces acting on it, gravity and the buoyant force. If we put something in a fluid and it sinks, we know that we have a net downwards force. It's going to accelerate downwards. We have this net downwards force. So the gravitational force is greater than the buoyant force. If something's floating, if it's not accelerating up or down, it's just floating like on our surface, we know that overall there's no net force acting on it, just like things that we've done with Newton's second law in the past. If our sum of forces is equal to 0, our acceleration is 0. So our buoyant force and our gravitational force would be equal, and our object would float. If we put something in water and it starts accelerating, or not water, any fluid, if we put something in a fluid and it starts accelerating upwards, that means that our buoyant force is greater than our gravitational force. So something like that would be like, hey, you stick it underwater, it's fully submerged, it has this upwards buoyant force. When you release it, it starts going upwards. We know that we have a net upwards force and a net upwards acceleration. And then what we said was, everything else before kind of flowed nicely. We're like, we did this, and then that did that, and that did that. Then we kind of did a little turning point, and we said, okay, everything we looked at before, our fluids were staying stationary. Now what we're looking at is fluids that are moving. We're looking at fluids that are in motion. So what we did to start this is we said, hey, let's try to get this fluid from this higher cup to this lower cup. And we kind of likened this to kicking a ball up a hill. We looked at it in terms of energy. We said, hey, if we want to get this ball up this hill, we have to get a little push. We have to do a little bit of work on it. And we said, hey, this is really similar to this water going up this hill. We worked a little bit with energy bar charts, and we came up to this idea that in a fluid's flow, energy is going to be conserved. We came up with this conservation of energy statement for a fluid, which is going to be referred to as Bernoulli's equation. This idea that in a fluid's flow, the pressure, the kinetic energy per volume, and the potential energy per volume is going to equal at some other point the pressure, the kinetic energy per volume, and the potential energy per volume. And we're kind of saying like, hey, these are equal. We have this equation that we're just going to use because we're going to say that for the most part, our systems are going to be contained. We're not going to have like outside pressures coming in that we have to worry about. We're just going to say this pressure exists in the pipe, and then kind of go from there. We're not going to have somebody like come and push on it like we saw with the work term in our energy equations. And then what we did was we applied this Bernoulli's equation to water coming out of a sink. And we said, okay, as the water got faster, we saw that as it went down, the area got smaller. So we had this idea like, hey, as the height decreased, the velocity got bigger. So I like the shocked face. It was like, whoa, it was crazy. So we saw, hey, as the height decreased, the velocity went up. As our velocity went up, the area went down. So then we said, okay, we kind of have this relationship between velocity and area. That's a little bit weird. And what we said was, hey, this is consistent. That's how you say words. I was going to go with continuity, but I want to say consistent first. This is consistent with the continuity equation, or in other words, this conservation of mass for a fluid. So we said, hey, when a fluid is flowing, this volume flow rate, this idea that the amount of volume that's flowing through a certain area over time has to be constant to make sure that the fluid is all flowing through our pipe. We said that the volume flow rate is constant throughout a fluid's motion. This volume flow rate is typically going to be represented by this area times velocity equals area times velocity. We didn't really do this. This isn't on the equation sheet, but it's a volume flow rate. So we can also define it as volume divided by time, the amount of volume that's going through a location per time. If you were to do volume divided by time or area times velocity, you see that those units will be the same. So it really represents the same quantity, right? Volume is meters cubed, time is in seconds, area times velocity, meters per second times, meters per second times meters squared, there we go. Meters cubed divided by seconds. So you see, these are representing the same quantity. These have the same units. It represents the same thing. It's just another way of stating it. We're not really going to use this volume per time, but just throwing it out there, volume flow rate, how much volume passes per time. We're going to really focus on this idea that A1V1 is equal to A2V2. And that is what I have for you. Not really, like we're going to do group stuff, but that was kind of my overview of what we did throughout the unit. So does anybody have any questions about that? Anything that you want me to go over again? Anything that's confusing? Oh, perfect timing. No, I'm just kidding. That's kind of mean. I guess I recorded it, so I can just send it to, okay, whatever. Yes, any questions about anything we have going on? Otherwise, I'll just I guess I'll just stop the recording. Should stop the recording. I'll just stop the recording and then we can answer questions anyway. Okay, recording stopped.